Okay, I didn't get a chance to look. How did my math lab go? Are these getting better? Are we kind of getting the hang of this thinking backwards? Okay, so that hopefully that was helpful.
Oh, yes.
This is what I wanted. Okay, so fundamental theorem of calculus, what does it say? It says that an open form accumulation function with rate of change f of x, and we all know what that is by now, right? Open form accumulation function. How do we express that?
Open form accumulation is an integral.
Is an integral, right? Is the integral, right? So the open form accumulation function rate of change f of x. Fundamental theorem says that it can be written in closed form. If what? So what's the qualification on that closed form? Capital F can be any function? Just any function?
The accumulation of
Okay, but what is that? Yeah, an antiderivative of a rate, right? So this is what the fundamental theorem says. It says that an open form accumulation function with a rate of change f can be written in closed form, where f is any antiderivative, big F is any antiderivative of little f, the rate. Okay, and so then if we evaluate that at x equals b, so that's a function, right? It's a function, and x represents where we're accumulating to, where we're stopping our accumulation and evaluating how much is accumulated. So if we evaluate that function at x equals b, what does that do? That yields the net change in the accumulating quantity from x equals a to b. So yes, write, but also think. Okay, yeah, write, but also think. So this is just basically plugging in b to the function, and what do you get? You get an amount of accumulation from a to b. So now there's a notation that I want to point out here that's often used as kind of a short way of representing this left-hand side here, or right-hand side, and that's just write the function, and then you put a vertical bar, and then x equals a, x equals b. And so that notation in red means exactly the same thing as capital F of b minus capital F of a. So you'll see that in my math lab, you'll see that in other textbooks. It's just kind of a shorthand way of writing the same thing. So 80% of the time we spent this semester has been related to understand building this and understanding it. Why? Because it has to do with, we used constant rate of change to build up how did we get accumulation from rate. And we summed up a bunch of little delta y's, right? And then we worked on derivatives in order, so having all these derivatives allows us now to get antiderivatives. And having antiderivatives allows us to write a closed form accumulation function from an open form accumulation function. So it's all this work that we did, a huge chunk of the semester was developing this very thing. Any questions? Okay, so let's do an example. So this is actually, we've seen this example before, but it was before we were able to write a closed form accumulation. So this was the stretch of highway. The rate of change, elevation with respect to distance, and this is in feet of elevation per mile of highway going east of the Utah border. So first, here's a graph of elevation. So is that a rate of change? If that's the graph of the change in elevation from the border as a function of the number of miles, is that an accumulation graph or a rate of change graph? That's our accumulation, which is changing at this rate, right? So that's changing at this rate. So we're interested in the accumulated change in elevation starting at mile 2 up to mile 5. So we'll look at that in two ways. First, how would you represent that on this graph? How would you represent that change in elevation on this graph from mile 2 to mile 5? Peter, what do you think?
You would plug in 2 for x and
Okay, and that's right. And how that what you just said, how is that represented on the graph?
Find the accumulation at 5 and subtract from that the accumulation at 2.
And so is that x coordinates, y coordinates, Chloe?
Well, yeah. Okay, so the y coordinate at 5.
Y coordinate 5. I'm going to do my best, very best horizontal line here.
And then minus the y coordinate at 2.
So the only thing that matters is if I end at the y-axis directly across. Okay? All right, so what can we make an estimate for that y coordinate at 5? Did I go down a little bit? No, and I came back up. So 480? I'm going to say 85. Okay, and then?
And then the y coordinate at 2.
And what's that about? Oh, that. All right, got 200 and 290. Those are decent estimates. Okay, and so the accumulated elevation from mile 2 to mile 5, just as purely as an estimating activity from looking at the graph, would be what? Aaron?
I'm sorry, what's the question?
So I'm just purely estimating the change in elevation from mile 2 to mile 5. How would we calculate that estimate?
Just subtract 290 from 4.
Yeah, 290. So let's do that. Let's get a rough estimate here before we actually use the calculus. So what is that? 95? Or 195. Okay, so just remember that. Can we remember that? 195 feet. Net change. Okay, how can we use the rate function to represent that accumulated change in elevation from mile 2 to mile 5? How can we use the rate function to estimate? Nicholas?
The integral from 2 to 5 of RT dt.
What do you think? Is it right? Yeah, and so then we know what that rate is, right? So we have a closed form rate, so we could put it right there. Okay, so let's work on that. So now we've got this fundamental theorem to actually calculate this without using graphs. So before we used graphing calculator and we put in the open form and it gave us a number, right? But now we can use the fundamental theorem to get the closed form and calculate closed form accumulation and calculate that net change using antiderivative. So let's do that. So there it is. Here's the rate that we just wrote down. So so one thing we saw with derivatives is if you have a constant times a derivative, or sorry, if you have a constant times a function and you took the derivative of it, then it was just, you just held on to the constant and took the derivative of the function, right? So that works forwards and backwards. So the first thing we can kind of do with this to make it easy on ourselves is just pull that 52.8 out. And then we'll have cosine x times e to the sine x plus 2. Okay, it's worth noting that you know, this function as a rate of change of elevation from the border is a little bit ridiculous. Okay, it's just worth noting, but it's just an example. Okay, so that you would model that with cosine and e functions is a little bit unrealistic, but it's just an example. Okay, it's just an example. Okay, so if we want to evaluate using the fundamental theorem, then what do we need? Steve, how can we make some progress on this to get a closed form net change?
Integrate it.
What's that?
I guess you could find the antiderivative.
Right, we'll need some antiderivative of this in order to find the net change using the f of b minus f of a way, right? So that's our goal here. We want to get an antiderivative and do this. Okay, so we look at this and we ask the question, what function is this the derivative of? We've got e to the sine x and cosine x. Can you recognize what function is this the derivative of? Austin.
E to the sine x.
He wants e to the sine x. And if we're not sure, what can we do? Take the derivative and compare it to this. And that process helps you to revise it. If it's wrong, that guess and check the derivative will help you to see how you need to change your guess. Okay? And so take the derivative, you get e to the sine x times by the chain rule. Derivative of sine is cosine. Perfect. Okay? Plus antiderivative of 2. So 2x. So we're asking, is the derivative of 2x 2? Yeah, that's it. So we'll have 52.8. And we've got our antiderivative. And so let's use that new notation. So this is saying evaluated at 2, evaluated at 5, and subtract. And that's our how do we do? Is it good? So I think that's exactly what we said. And so what do? We plug 5 in and evaluate it, and plug 2 in and evaluate it, and that gets, this is our net change and accumulation, because this antiderivative is our accumulation function for that rate.
How come you don't use the
What's that?
we don't use the function for e sine?
Not sure what you mean. Are you talking about finding the antiderivative of this? Or expressing this? Or go ahead. So which line are you, is it this right here?
Wait, how come it's not e sine x times cosine?
Okay, well let's do the derivative of that. So how would you do the derivative of e to the sine x times cosine x? What would that entail, doing the derivative of that? Be product rule, right? It'd be long, and it'd be really long. It'd be something, derivative of that times that, plus derivative of that times that. And that's not going to be that, right? So this is basically the result of the chain rule. And so if you took the derivative of that, e to the something, its derivative is e to the something times the derivative of the plugged in, which is there. Is it better? Okay, so now this is evaluating it, and 548 minus 342, and how was our estimate? Pretty good. We said 195. It's about 206. Okay, any questions on this example of using the fundamental theorem to calculate a net accumulation? Does it make sense? Okay, another example. So a culture population in a particular dish has an initial population of 250 cells, grows at a rate of 50 e to the 0.3 t cells per day. And that's a realistic way. So using an exponential function to represent the growth of bacteria, that's more realistic, okay? So we want to find a function, b of t, that gives the population at any time t greater than 0. So, get me started. Any ideas? How are we going to write this function, capital B of t? Sterling.
Is it 50 e to the 0.3t?
Okay, so tell me what you're thinking. So you're saying that you're trying to write what bt is?
Yeah, derivative of e to the x is e to the x.
Okay. So it sounds like you're trying to find an antiderivative of this. Is that right?
Yeah.
Okay. So before we do can we write open form? Can we write an open form version of b of t? What would that be? How about somebody new? Kevin, you write open form?
I think it might be the integral.
Integral?
0 to 10, I believe,
Because 10 days after.
No, so we want any time t. So we want function.
Okay, so the integral of 50e to the point 3t.
Okay?
And then I believe it would be t of t.
dt. Okay? All right, so if we want the input of our function to be t, so we're gonna write this from what to what. Okay, so if we want the input of our function to be t, we want to go from what to what?
250 to t?
Okay, so 250 to t. What do we think about that?
0 to x.
Yeah, so 250 is a number of cells, and these limits would be what quantity? These would be time quantities, right? So I heard from 0 to t, right? Because those should match. Now, so now what about this now?
Should change that for x.
Yeah, we need to change this to something else. So anything you want.
W.
What's that?
W.
I'll use w later, so how about something else? Z. Because you're not falling asleep. Right. Okay, so let's do z. All right, so here we go. Now let's talk about this. So this accumulation function, what is having the initial limit here of 0 do to this accumulation function? Remember this? Yeah, it's going to reset at 0. Okay, it's going to reset at 0. So therefore, if we were to plug 0 into this, how many bacteria would we have? From the way we've written it, if you plug 0 into this b function, what are you going to get? You're going to get 0, because it's going to have this rate function starts way out at negative infinity. But the way that we've set up the accumulation function, it's going to end up at 0 being 0. So is this correct for the capital B function that we want? So how can we make an adjustment to the capital B? Yeah.
Can you add 250 to it?
Yeah, so we can just take that and just add 250. Knowing that the way we set it up gives us 0 at 0. Because it gives us 0 bacteria at 0 days. So now that forces, with this rate function, at 0 for B to be 250. Okay, now we want to write it in closed form. So this is now going back to Stirling. So antiderivative. I think what you said was this, if I remember right. Is that what I heard you say? Yeah. Okay, so now, is it right? And how can we know if it's right? Marco. So this has been offered up as the antiderivative. Take the derivative of that. Okay, so what would the derivative of this be? You do it?
Would it be...
Uh-oh. Mastery test. Don't forget it. That's why you wanted to be a master, right? Is so that we could do these. Yeah. 50e.
15.
Where's the 15 going to come from? So you're from the beginning, you're seeing you're going to have to multiply by 0.03. Is that what you're saying? All right. So can we just do that? Let's do that at the end. So 50e to the...
e to the 0.3z.
And then?
And then times the 0.03.
So we compare. Is that the same as that? No, it's different because of this factor right there. So we need to adjust this a first attempt. What do we need to do to adjust this so that if we took the derivative of it, we get exactly that. We wouldn't have this 0.3 anymore.
You wish to divide by 0.3?
Yeah, so we could take a 1 over 0.3 with it. And then we would get, for that part of it, we'd get this, and then we'd multiply by 1 over 0.3, and it would go away, and we'd have that rate. Okay, and then that's going to be from 0 to t, and we're adding 250. Did you catch it? So this is getting into the harder ones. At the end of class today, we're going to be working on harder antiderivatives, which are undoing the chain rule. Okay, undoing the chain rule. Those get harder. So this is kind of a bridge, or kind of moving towards more difficult ones. Any questions? Yeah?
Yeah, why in the previous problem did we pull the 52.8 out as a constant, but with this one we left the 50 as part of it?
Because that was a sum. We could have in this one too, but because it just didn't really save us any time in this case. Yeah, we absolutely could have. Absolutely could have. Yeah, Ross.
Well, so far, most of the antiderivatives we've been using are either chain rule or addition. Are we going to have to undo multiplication and addition rules?
That's Calc 2.
Okay.
Yeah, that's yeah. Undoing the product rule is something called the parts formula. So parts is basically using integration by parts is undoing the product rule, but that's not in this course. Yeah.
I don't understand how in this one you didn't pull out the sign on the E part.
Say it again.
On the last one you didn't pull out the sign or cosine, I can't remember which one it was, but then this time you did pull out the 0.3 and put it on the side.
It's all about getting a function whose this is the mindset you have to have. It's all about getting a final function whose derivative is what you're starting with. So it's about really understanding derivatives really, really well and being able to see them in reverse. So don't try to come up with a new set of rules for antiderivatives. That's what kind of sounds like you're doing. It's all so. If we took the derivative of this, do we get that? That's the bottom line. So it kind of sounds like you want new rules for antiderivatives when it's really we're using all the derivative rules and in reverse. So we could, after class, if you want to look at the two examples, we could work on it. Okay, so what do we got? So then we're going to do 50 e to the 0.3t. So let's simplify this. What is 50 over 0.3? That would be, what, 10 thirds? 500 thirds? Perfect. All right, with t plugged in, and then with 0 plugged in. Now watch out. You don't get 0 in every function that you plug 0 into. Here's an example. What do you get in this case?
500.
Yeah, so you get e to the 0, which is 1. So that's students make that mistake often. They think that because you're plugging in 0, you're going to get 0. That's true for polynomials sometimes, okay, but not e functions. So plug in the 0 and evaluate it. Okay, so there's our b function. And how could we find then the bacteria population after 10 days? How do we do it? Mackenzie. So now I want to know exactly how many bacteria I have after 10 days.
Why don't you just plug in 10 for T?
B of 10. B of 10. Okay? All right, questions on this example? Does it make sense? Yeah.
Do you have to do the simplification, or could you just leave it like the middle one?
Yeah.
Do you have to,
Which
like, do you know how on the second row that was the answer, but then you simplified it to like
yeah, so this still okay, so yeah, we want to get a closed form. We want a closed form for capital B. Yeah, so we go ahead and put T in 0. You guys good?
Yeah, why do you have 500 over 3 e to the 0? No,
So what this right here is, so we got
so is that just
it's f of t. We're doing f of t minus f of 0 is the fundamental theorem, right? It's
Yeah.
the difference in accumulation.
Oh, okay.
So I'm plugging 0 into this expression,
Okay, that makes sense.
and that's that right there. And then adding the 250. Okay, other questions? All right. So it's we're kind of all crunched in here at the end of the semester. Usually the semester ends on a Tuesday, and we have the last exam on Thursday, and then we have a Friday and Monday. So we're all crunched in here at the end. So what I'm going to do, because you need it for preparation for the final, and I think the success rate has been very high on my math lab, so it's going to help your grade too. So we're going to have a couple sets due Monday, even though the last day is Friday. Okay. And that's to help you prepare for the final and help your homework grade. Okay? Yeah.
I went on my math lab to do like the 2 problems, and then it wasn't like it showed up like 11 problems, and I would click on each one of them that says file not found.
Well, so that's a different. We gotta.
That's okay.
Yeah, so you can go to the customer support for the website. That's some kind of computer error. Yeah, so when, yeah.
Was it 2 problems or 11? Homework. Because I had 11 problems.
Yeah, 11 problems.
Okay.
Yeah.
Well, online is 2 problems.
No, so that's just the per problem, how many attempts you got. So sometimes you remember in the past I've given you 1 attempt per problem with 3 tries. I was just saying now you got 2 per problem, so 3 tries each, or 6 tries. Question?
Well, just a homework thing, because it's more like kind of a personal one, but it's just the one where you had to do the create where you specify what the C was.
Okay.
Because one of my problems ended up, I tried doing it and I did it the way it was the answer, but it said it was wrong.
Okay.
So then I tried converting it into a decimal fraction since it was over 2. So I converted it to 0.5 and it still gave me the wrong. It still said it was wrong.
Okay, so let's talk about it outside of class, or you can go back to it and try approach it this way. This is a slightly different way of approaching it. And so what happens when you do this? So at 0, we wanted 250, so we just started integrating from 0, and then we added 250 to make sure that at 0 we get 250. And so then your constant ends up being all this stuff right here. There's your C. So you could try this approach to that same problem. And then this right here is your C. Does that make sense?
I think so.
So rather than doing an improper integral and having a plus C and then going back and solving for C, set up the open form as the exact function that you want. And then once you solve the closed form, then your C is whatever is left over here. Does that make sense? Yeah. Okay. Other questions? All right. So let's make sense of more complicated expressions. So here's a more complicated expression. It's the rate of change with respect to x of the integral from 4 to 7 of sine of 3 cosine x dx. It's like just all these symbols, right? And so we really want to focus on what does this mean? What does this mean? So what's rate of change? The whole thing is a rate of change. What? Okay, so she's looking at these first symbols and saying this is finding the rate of change. That's doing the rate of change of all of this. Is that what you're saying?
I would say that is.
Right, yeah, so the whole thing is this is the rate of change of this right here. Is that right? Okay, what else? What else? What other meanings do we have in here? Christian?
We know that integral from 4 to 7 sine 3 cosine of x dx is an accumulation function.
Okay, isn't it? See, he said that this, so now don't look at the dx, so this right here, I'll do it in blue. He's saying this is he said this is an accumulation function. What do you think? Lots of nods. Is it an accumulation function? Still nods. It's not an accumulation function. Why not? No. What's it, Molly?
The part inside, sine 3 cosine dx, that's a rate.
That's a rate. Okay, that's a rate right there. That's a rate function right there. But the whole thing I put a blue box around, is it an accumulation function? It's a value, right? That's a value, a net change. It's a value of net change. Why is it that and not an accumulation function? Yeah, so we're accumulating from 4 to 7 at this rate. Right? We're accumulating from 4 to 7 at this rate. So it's not a function, it's a value of a rate of net change. Okay, and so then Melody said, it's the rate of change of this thing in the blue box. It's the rate of change of this. Alexander, what's that?
It's going to be a loss question.
So if the whole blue box is a value, it's a number, like, right? It's an amount of accumulation from 4 to 7 at that rate. And now we're going to find the rate of change of that value. What will it be?
Inside, sine 3 cosine x.
No, Steve.
0.
0. Why 0?
Because the derivative of a constant is 0.
Yeah. Did you see it? Yeah, so this whole thing, because it's not a function, it's just a value. It's a net accumulation is a number. Just like 206 feet of net accumulated feet, was that, right? And so if you take the rate of change of a constant value, it's 0. Okay, so maybe more interesting is this question then. How is this different? Aaron?
This would be an accumulation now.
Be more specific. What would be an accumulation?
The integral of x before sine 3 cosine t dt.
Okay.
All that is an accumulation now because you have x as your I don't know. I don't know now.
Jonathan?
Since x is what you're integrating to, so you're doing your set accumulation from 4 to whatever value x happens to be.
Okay.
So that becomes an accumulation function.
And now it's a function, right? Yeah. And so now we want to take the rate of change of that accumulation function. That's what this is, right? Okay, so how about here's our rate. What about an antiderivative of that? What about an antiderivative of sine of 3 cosine t?
I have a question.
Yeah, sure.
Do you even have to find an antiderivative of it? Because if you're finding the derivative of the antiderivative, it's
Uh-huh.
kind of like canceling each other.
Okay.
It's like a
I
double
think
negative.
he's on to something there. Okay, so we're taking the rate of change, or the derivative of an accumulation function, or an antiderivative.
You seem really fun.
Okay, Ross, what were you going to say?
I was just going to say the same thing.
Same thing. Okay, so what about this is a good point, and we'll see that. What about this question of, what about an antiderivative of sine of 3 cosine t? Is there a function whose derivative is this? Is there a closed form function whose derivative is this? Well, let's look at sine. So maybe
Would that be like a composite function?
maybe negative cosine, right? Because the derivative of negative cosine is sine, right? So maybe negative cosine of 3 cosine t. How about that?
Divided by 3. Yeah, divided
Okay, divided by what?
3 cosine t. I mean, 3 sine. Negative 3 sine t.
Okay, so how can we check it? Take the derivative. And how do we take the derivative of that?
It's a
Quotient rule. Is it this? No. Doesn't work, right? It doesn't work. And so the point is, for this rate function does not have a closed form antiderivative. There is no function whose derivative is this function. Okay? There is no closed form function that if you did the mastery rules, you would get this. Okay? And in fact, of all the functions in the universe, a vast majority are like this. A vast majority of functions are like this, that there is no closed form antiderivative. Why? Because functions that have a closed form antiderivative are very special, because they're the derivative of another function. You see? So if you just had all the functions in the universe, most of them would be like this. They would not have a closed form. Every one we've given you was the result of a derivative, right? So it was rigged. And that's why we could find the antiderivative, because it was the derivative of something else. But if you look at the sum total of all functions, well, most of them would be like this. They would just be, take a random function. It's not, in all likelihood, going to be the derivative of another function. Okay, so anyway, that's just kind of a side note, but an important side note. So, but we can kind of pretend that it exists, right? So call the antiderivative f of x. So we're pretending that there is an antiderivative. So then, what would it be? we would have d dx of what? So we have an antiderivative, capital F. What does this equal in terms of capital F? Connor.
What was the question?
So I just got done with a speech saying that this rate does not have a closed form antiderivative. But we're going to pretend it does, and we're going to call it capital F. So then what would this equal in terms of capital F? Nope. Brent.
Is it f of x minus f of 4?
F of x minus f4. Fundamental theorem, right? Okay, so then we have dfx over dx. So we want the rate of change of f of x. What's the rate of change of f of x? Sine of 3 cosine x. And what's the rate of change of that antiderivative with 4 plugged in? 0. Okay, so the hypothesis was right. We had a rate function. We found an accumulation function, and we wanted the rate of that accumulation function, for which this was the rate. There it is. Sine of 3 cosine x. But, so be careful. This process is very important, as we're going to see in a future example here. Still have to understand this process. Did you catch that? Yeah, Kevin.
So that process you just did,
Uh-huh.
it's just like proving what they were trying to say over there.
Yeah, it shows right. It does. Other questions on that example? So here's prettier version. That's what we said.
So does that work for any like function? Like, so even if it did have an antiderivative, could we use this method to find it?
If you're eventually taking the rate, yeah. If you're coming back and taking the rate of it in the end.
Okay.
Okay, how about this one? What does it mean? So let's take a minute and talk about this and see if we can make some headway on this one. Talk through this. You tired?
I've been studying so much.
For
Chem test, your math test Friday, Thursday, and then finals Monday, Tuesday. It's been a long week.
Okay. So, Linwin. So, can you answer this question? This in parentheses here. What kind of function is this right here?
Maybe it's the derivative of the rate.
Derivative of the rate. Okay. So, what kind of function do we take the integral of? So, if we have an integral of a function, what is that function right there? What kind of function is that? It's rate, right? So does that follow here, that this is a rate? Yeah, because it's a derivative of something, right? It's a derivative of something. So if we're going to use the fundamental theorem, what do we need? If we're going to use the fundamental theorem to rewrite this rate function, what do we need? Antiderivative, right? So here's our rate function. We need any antiderivative, right? Any antiderivative will work. So what is an antiderivative of this rate function? Yeah.
Sine of 3 cosine of x plus like 24.
We're not setting this up yet. We're just doing the what is an antiderivative we can use in the. I think you're jumping ahead a little bit. I think. So what is an antiderivative that we can use in the fundamental theorem?
Like what kind?
Yeah. So okay. So capital F of t minus capital F of 4, right? So now we need an antiderivative. Do we have an antiderivative of this rate function?
Yes, sine of 3 cosine.
What is it, right?
Sine of 3 cosine.
Yes. And we can, any one we want. So let's just use sine of 3 cosine x. So we're plugging in t and plugging in 4. Right, so if we're taking the rate of change of this function, then that function is an antiderivative of the one we took the derivative of. And we're going to evaluate that at t, evaluate that at 4, and subtract. So really practicing meanings of these expressions and practicing the fundamental theorem. Any questions? Let's do a harder one. Yeah, Alexander.
I still don't understand why sine of 3 cosine t is the antiderivative of sine of 3 cosine x.
No, it's the antiderivative of the derivative of that. See? It's the antiderivative of the derivative of that function. So this is not the antiderivative of sine cos 3 cosine of x. It's the antiderivative of the derivative of that.
Okay.
You see? Kevin.
So the difference between like the second problem we did and like the third one is just like it's not like the answer, but just like the way we got there basically. Like
No, this says take the rate of change of this open form accumulation function.
Okay.
This is an accumulation of a rate.
Okay.
So it's
you're giving us the rate already, and that one, the top one saying take the rate of the accumulation function basically.
So this starts with a function, and we create a rate of change function out of it, and then we form an accumulation from 4 to t out of that rate function.
Yeah.
This one is we start with a rate, and we've got an accumulation function from 4 to x, and we take the rate of change of it. See? So it's like an order.
Yeah.
Okay, so let's try something that really tests to see if you got it. So there's the prettier version of that. Okay, go. See if you can do it.
Yes.
And let me just note, this is another one that does not have a closed form antiderivative. Is that a question, or?
Just wondering, for future references, like for like maybe our exams or anything, like, will you tell us that this is not close? This
No.
So what do you want from this?
The answer. But you have to apply the process. This one is different. If you don't apply the process and you just going for a fast track, you're not going to get it correct. Got to think through that process. Okay, so if capital F is an antiderivative of square root of 1 plus w squared. Yeah, why don't you take a minute to check. If you want to check with somebody else, talk for a moment, see what you came up with. Okay, Bowen, did you get it? Did you guys get a first step? Still working on it. Ariana, did you get a first step? How about this? Are those two things equal? Derivative of that, yeah. Good first step. Danny, next, go for it from there.
And then I took the derivative of each individual term.
Okay. So can I plug in this step? So save some room here. So what is capital F of e to the 4x? What is capital F of e to, oh, right, we don't know what that is. All right, so.
The function for e to the 4x.
Yeah, sorry. I don't know what I was thinking. Okay. Okay. Now what? What is the derivative with respect to x of f of e to the 4x? Yeah, Gilbert.
Radical 1 plus e to the 4x squared.
Okay. Minus 0. Agree? You agree?
Yeah.
Aaron?
The derivative is the square root of 1 plus w squared.
Well, but the w is, these are w values, right, that we plugged in.
Yes.
Derivative of capital F of e to the 4x. Is it this?
No,
Oh, tell me.
but I don't know how to read it. I can write it.
Okay.
But yeah.
Does it have this in it?
What?
Is this part of it?
No,
This isn't part of it.
it's 4e to 8x.
I think we've got a good start, but this isn't complete. Why not? Aaron? What's that? We're integrating with respect to x now, right? Gilbert?
There's a chain rule.
Yeah, so we're doing...
see where it's gonna come from. I know it's the e to the 4x, but it's also squared, so I think it's gonna be 8 e to the times 8e to the 4x. No.
You're on the right track. So it's chain rule. We got chain rule. See, we're taking the derivative of this.
One over 2 square root 1 plus e 4x plus squared times the derivative of the e to 4x.
Okay, so let's look at this in blue here. The derivative of this is f prime with e to the 4x as it is. Then what? Times the derivative of that, which is 4e to the 4x. So you take the derivative, leaving the inside function as it is. Right? This is just the same chain rule we did in the mastery exam. Taking the derivative of this function with that plugged in. Well, the derivative of that with that plugged in is our rate function with that thing plugged in, which is what we have. But then by the chain rule, you need, with respect to x, you need times 4e to the 4x.
But you don't do the derivative of the square root?
The square root is the rate of change function. So this here is that square root function. But it's not of w, it's of that. See, this is that rate of change function. It's this. But now it's not f prime of w, it's f prime of that. So it's going to be e to the 4x squared.
So it's like you were missing part of it.
No, it's
And then eventually you did and you added it.
no, it's you're taking the derivative of the argument, which is in the inside part. So it's like, yeah.
Okay, if you want to keep talking about it,
See if I can white track.
can we just see if anyone wants to? Does anybody else want to talk about this problem? Question about that? Does it make sense? You do? Let's go. Instead of changing the subject, let's.
So if you're going to talk about this problem, can you record it?
I'm still recording. I'm still recording. Yes, I'm still recording.
So this is like a chain rule.
This is exactly the chain rule. And why do we know the chain rule? Because of this right here. Okay. So there's some antiderivative of this, right? And we're plugging 4x into that antiderivative. We're taking the derivative of that, which we know is that, but with that plugged in. We're taking the derivative of that of a function. You need to use the chain. You need to chain on the derivative of the inside.
Okay.
Is it better?
Yeah. You read about the not just.
Yeah, you gotta know what's going on. You can't just assume an answer. Who's Zoe? Is it?
I'm just looking. See where I'm at.